afternoon. Welcome to Osmosis, the podcast where we talk about science, scientific papers, and hopefully we all learn something along the way. My name is Callum Morris, and your name is?
I'm Jamie McMillan.
Excellent. How are you doing today, baby Jamie?
I'm pretty good. This has been a really fun one to prep for. I felt like I learned a lot. I feel like maybe my perspective of a field of science has changed.
Interesting. I'm excited to osmosize your experiences and learn. I just muted myself. Can you hear me?
Oh yeah.
Excellent. I don't know when I'm muted, but I'm just going to assume it's
Just
fine.
then. Yeah. I'm looking forward to unpacking. Should be good.
Excellent. So, for those that are viewing the video, I've got the paper open on the side. We are talking about a paper from 3rd of April 24. This is DESI 2024-3, baryon acoustic oscillations from galaxies and quasars, and then DESI collaboration. And there's a long list of collaborators. And this is from the archive, right?
Yep. We're taking another trip to the archive this week. This was a pretty fresh paper.
Yeah.
I say paper, it's kind of like a collection of papers. They released a whole swathe of
Information, data.
Mm.
Yeah, lots to unpack. So before we hit recording, I was going to tell you what my prep has looked like for this. So I read the abstract, I've read the conclusion, I skipped 100 pages in between. I've done my best to sort of watch some videos because I wasn't even familiar with what DESI stands for, which I believe,
me either.
You can correct me if I'm wrong, dark energy spectroscopic imaging.
I don't know. I don't know. I think it was. I can't remember actually. I made a note of it, but I can't remember. Yeah, let's assume you're right. Probably.
We'll assume. You should never assume. It makes an arse out of you and me.
Yeah, let's just not do that. But what it actually is it's like an add-on. You could think of it like a plug-in for your telescope. So you got a big old telescope, and it's sitting on the top of the mountain, and this is a plug-in.
Nice.
It gives you a bunch more data. Well, rather, it takes your telescope measurements and does lots of cool stuff with it.
Yeah.
So you read those bits.
I read.
What did you make of it? What were you? What did you? Yeah. What did you learn? What do you think the paper's about?
So the paper is about. It's basically just taking another look at sort of very deep space, which is going to get me all philosophical because when deep space is obviously in the past. Although is it even in the past because it's presently getting to us? Ooh, who knows? It's very philosophical, but we're effectively looking at remnants of the Big Bang, and there are some interesting sort of takeaways and things. I understand that in the paper they're looking at lots of different historic things and sort of comparing it with sort of what DESI has done. To sort of increase, I guess, accuracy and reliability in the data. I'm not really sure, to be honest, but that's my understanding of what we're looking at here.
Nice. Yeah. What did I call as the takeaway? So the paper is broadly. My takeaway was it's. So it's doing it's doing a lot of stuff here. So this is big paper. It's more like a report than a typical paper. It's trying to answer some of the fundamental questions for cosmology, the field of cosmology at the moment, which is the universe expanding at a accelerated rate? Is its expansion changing over time, or is it just constantly expanding? That's what it's trying to answer, and it does.
They're very big questions. They're very big questions, aren't they?
Yeah, which in the field of cosmology, where the only thing you can do is look at things.
Yeah,
That's a big question to figure out. I can't go and poke it and take it into a like scanning electron microscope or
No.
do some chromatography on it.
Nope.
No, I just look at things. That's it.
And take
So
away from what you see. Exactly.
yeah, so massive respect for getting well,
Good
getting as
science
much
is
stuff as they can
observation,
from
right?
us.
It's mad, and I think about sort of how large the team is just on
Mm-hmm.
this collection of
Mm-hmm.
papers alone. You know, it's loads of people, loads of
Yeah.
people.
Yeah.
So this is a big job.
Agreed. So I think. Hmm. So oh man, I can't even step into it. I'm trying to find a neat step in.
So I think a nice place to start would be to talk about galactic redshift. I think that's a good
Okay,
place to
I
start,
like that.
and then we can sort of explore, because that I think that's quite a simple concept, um,
Yes.
compared to thinking about the big cosmological questions. So let's
Yeah.
start
All right.
there.
Let's start small. The so the paper's trying to answer how is the universe expanding. One way you can do this is by looking at
Very far away objects.
you can look at really far away objects, but you can look at near objects as well. So a characteristic component of the light that we see is it has light of very distinct wavelengths. So, for instance, like a star might have most stars would have a characteristic light or wavelength that they emit at, and that's what they emit at. But when we observe them, that light might look a little bit different.
So
And
the
so this
way,
phenomenon is yes,
so I think that we're talking about absorption spectra, right?
yes,
We're kind of getting
yeah, that
along
type of
those
thing.
lines. So when you the way so this comes up a little bit in like higher tier GCSE when you talk about absorption spectra when you do waves and light and things. And I almost describe it as like a fingerprint of the elements that the thing is made from. So like if you look at our sun, there's like an absorption line for like the hydrogen and for the helium, right?
Yes.
And
Yeah.
those lines move, like the barcode of those lines stays
Mm-hmm.
constant, but it shifts along the spectrum depending on where the object you're looking at is. So I've got a handy dandy little picture here, um,
Oh.
and this is just for so that people that are watching on YouTube don't just have to look at my face; they can look at the handy dandy picture. Um, so what we're seeing, it might be better to start with the Doppler shift, right? The
Mm-hmm.
Doppler
I
effect.
think
So
that's a great place to
so
start.
I always think about race cars when they're coming towards you, the frequency increases, and as they move away from you, the frequency decreases. So you get that like that, right? Like that. Um, don't judge me. It makes sense, right? So the when objects are moving closer, those sound waves are squishing together. And the
Mm-hmm.
closer it's getting, and if it's speeding up, they're going to get more squished. And if the frequency is more squished, it's higher in pitch, right? So if
Yes.
we translate that to light, higher frequency would be more blue or
Mm-hmm.
more indigo, more violet. Likewise, when it moves away, as it passes you, the frequency drops. That's because the car is emitting constant waves, but because the car's moving, those waves are reaching you slower. So
Yeah.
what we get is a shift the opposite way towards a lower pitch, or if we're talking about light, towards the red,
Yeah. Yeah. So we
right?
call that redshift.
Yeah.
And so
So
it uh, it will often manifest itself in a lot of the galaxies that we look at in the universe. They just look quite red, and they might not actually be redder, but they're because a lot of them are moving away. They just look quite
yeah,
red.
and that's the key, right? Is the fact that they are moving away from us.
Mm-hmm. Mm-hmm.
Yeah.
So if we look at things in our local cluster, so nearby galaxies, they might not be moving away from us. Like in our like local galactic community, things might be moving a little bit closer to us or faster to us. So you might get some blue shift in the local vicinity, but when we're talking big picture, looking at galaxies further away, then the broad picture is everything's red, everything's moving away, everything's expanding. So the space-time fabric is it the space-time fabric? But at least the space fabric is all just stretching. You can think of it like a big like sheet of elastic, and people are pulling all four corners.
I always imagine you put a chocolate chip dough in the oven, and it all expands from every position at once. So it doesn't matter which chocolate chip you're sitting on, you will feel like the center of the universe, right? Because everything moves away from you at a static rate, which is why I can kind of understand why humans thought they were the center of the universe for so long, because observationally, that's what you see.
Yeah.
Though retrograde is a whole other kettle of fish. Spinning in the sky.
If we look at galaxies further away, then we see a larger red shift, which just means they look redder. And so you can put a plot together where you could plot like the red shift of a bunch of galaxies and time. And so the greater that redshift, the redder a galaxy is, the further in time they are. And so I pulled out a cool plot here, which no one else can see, but I can see.
Right. So we're on redshift. How far down am I scrolling?
I don't know. There's a plot, maybe about halfway down. Look back time by redshift, and I can see a red line plot with billions of years ago in redshift.
Yep, got it.
And I thought this was quite nice. So the redshift range we're looking at in this paper is about 2.1 arbitrary. It's not an arbitrary unit. It is a unit, but and you can see the unit in the x-axis here. It's like the difference between, it's unitless difference between expected and observed wavelength divided by the expected wavelength.
Yeah, so it's just a ratio, I suppose.
Yes, yeah, it's like a ratio unit. And so from between 0 and 2.1 is the range of objects, so galaxies and quasars, that this paper has surveyed. And if we plot that on the graph, we can see it's about 10.5 billion years ago. So so this is a survey of objects in our universe, and the DESI survey has been looking at things that come from 10.5 billion years ago, which I think that's crazy.
It's a long time.
It's crazy.
It's a long time. So I've lost my train of thought now. So we're talking about redshift.
Yep.
We've talked about how it is sort of linked with time. And am I right in saying that sort of some of the interesting questions that this paper looks to answer are things like, why do we observe, why the further away things are we observing more redshift? Because that would imply that the expansion is accelerating, which logically you wouldn't think, right?
I think it's the other way around.
Well, there's
the nearer things. Yeah, the more recent things are, they're expanding quicker. It's that way around.
Right.
But yes, like the statement that you were going to go on to say is, you wouldn't expect things to be expanding faster now than they were long.
Yeah.
Yes.
Doesn't make logical sense, does it? So what the heck is going on? And
so if we just step back to like why the universe is expanding, so can you say a few words on the Big Bang? Why is there a Big Bang?
So Big Bang, imagine all of everything is in a singular point in space and time, and then it gets, a bit too much and it just goes kaboom. And then everything that's in that is spat out in all directions, and eventually, it's very hot at the beginning and it cools down and things coalesce and matter comes together thanks to gravity, and we get stars and planets. And then fast forward a few billion years, little rat people running around trying to burn the planet to the ground.
Then there's us.
That we were the little rat people trying to burn the planet to the ground, by the way. I mean, maybe there is like an alien race of rat people somewhere out there as well. That would be interesting.
That would be good. So there's the idea of the Big Bang is everything started small and got big. And if you intuitively think about like an explosion, it goes boom,
And then it
and then
slows
just
down.
sort of like slows down and gets to a nice happy equilibrium
Yep.
size,
Yep.
maybe.
Yep.
But the measurements that started back in the early 20th century from like Hubble's discovery of redshift. I think although this, how long? Maybe it's only been in the last 20 years or so that people have been discovering that it's expanding. So redshift's been around for the last century or so, but where people have been measuring and surveying redshift, like with respect to time, they've been noticing that more recently it's been expanding quicker, or at least it was expanding. It's expanding quicker now than it was longer ago in time, and that is nuts. That
Accurate
is nuts.
scientific
Yeah.
description there. Yeah, it's bizarre. And so this is, so again, I'm going to link back in with the paper now. So dark energy
Please.
spectroscopic imaging. So dark energy is, my understanding of dark energy is that basically we look at all of the matter and all of the energy, and it only accounts for X% of what must be there for our understanding of gravity to make sense. So,
I think this is more, the dark matter side, but yes.
but I understand that empty percent is like dark matter and dark energy.
Is it?
I honestly don't understand
Maybe it
very
is.
much though.
I think it's better to like decouple them first. I think they're somewhat linked, but not. They're both
Not as
dark, but they're not
intrinsic.
super
Okay.
coupled. So yeah, if you account for all matter and how like the gravitational forces should behave, then there
must
is a
be more.
mystery amount of mass somewhere that we can't see, and that's dark matter.
So dark energy, then you can.
So
tell
dark
me.
energies. So if we're like discussing the rate of expansion, so something is pushing the universe further apart, faster apart. That
Right.
energy
Must
coming from somewhere, and that's an unknown.
So I
that's dark
I
energy.
watched a really interesting video. It was Neil deGrasse Tyson talking about it, and
What a dude!
I love him, and he was talking about how could it be that this dark energy is just another universe in the multiverse having a gravitational effect. And he was like there's, we can't prove it, but like philosophically and scientifically it's not a bad hypothesis, right? It would make a certain degree of sense if there was more. And this is kind of a weird, I feel like this is a really weird what's the word I'm looking for, where it's like what's the word, Jamie? Paradox. It's like a really weird paradox of looking into the sky. Is there's like a finite limit of how far away we can see, which is the observable universe, right? We can't see anything else because there hasn't been enough time for light to reach us, right?
Yep.
I like to imagine that there's just Jesus sitting outside the observable universe watching us going, don't oh well, actually I was going to make a joke then, but then I remembered we tag this as clean on YouTube, so I'm not going to do it. But I like to imagine he's just sitting there watching the human race outside the observer. It's like in his hands, you know. But yeah, it's great. It's a weird paradox because like we can't ever see what's the other side, right? I mean, maybe in a few hundred years we'll figure it out a way.
I can't think of any way to probe it scientifically.
Magic.
Like light's the best thing that we've got, and light's just not that quick.
It's pretty quick though, just not quick enough.
It's got a speed limit.
It has got a speed limit, and it never breaks the speed limit. It's the
No,
best.
but interestingly, if you look at
in the universe,
the expansion rate of the universe, I think at some points it's going faster than the speed of light.
Really?
Yeah.
That's weird, man. I didn't know that.
So everything in the universe has got a speed limit, but the universe itself, no speed limit.
That's crazy, man. That's crazy. I don't. Yeah, that's mad.
Yep.
That's absolutely mad. Shall we talk about the telescope itself? I've got the nice picture here that you sent me.
Yes.
So I'm going to have that up for any video viewers. But it is a beautiful piece of kit, isn't it?
Yeah, we'll pop some links in the show notes too.
Definitely.
Some pictures and videos, because like you take the paper as it is and you're like, it's cool. You're talking about dark energy stuff. This is all quite, I don't know, it feels quite theoretical. It's not, but it feels quite intangible.
It
But
feels
yeah,
very
was checking out some of these resources, and the engineering prowess that goes into this is just.
So I haven't got the article you linked to me open. I've just got the picture here. Do you want to take a little bit of time to talk about some of that engineering prowess?
Yeah. So, what are you looking at your image? What can you see?
It's the big picture of the telescope. You know, the one you linked.
Okay. Okay. Yeah. So
Images of the
DESI
DESI
is
kit and telescope.
DESI is like a piece of kit that's like plugged into the end of the telescope. So the telescope is doing normal telescope things. It's looking at things really far away. It can move. It can look at a bunch of things. It's ground based. It's not in space. But what the DESI instrument is doing is it's a spectrograph, I believe. Yes. So it's a spectrograph. So it's looking at, if you think of it as taking like a picture, it's taking a picture in multiple wavelengths. So like our normal cameras, they take pictures in 3 wavelengths, red, green and blue, and they kind of stitch it all together. And it's also got some near infrared bands, so it's taking a couple of wavelengths. It's doing that 5,000 times across the array, or like the aperture of the telescope. So it's got 5,000 robots.
Yeah.
Robotically controlled fiber elements. So these fibers are placed onto the. I don't know what it's placed onto, but they're controlled, and they control the observations and what's being captured.
Is it correct that each of those individual 5,000 fiber elements points at a different object? Is that what I understood?
Yeah.
That's
yes.
mad.
So like if you're thinking of your field of view, you've got a 4-meter telescope. You're looking into space. There's a lot of dead space, but there's also within there a bunch of galaxies. And if you divide your field of view into like 5,000 little quadrants, and you can you can look in each of those little quadrants, that's what those robots are doing. They're like saying, well, I want to look at this slightly different position in this quadrant, so then I will capture this particular galaxy that I know is there. I've
it's working on it already.
I know it's there. I know where it is. I want to look at that.
That's it is a.
And so yeah, they're robotically like boop, 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 boop.
It's almost science fiction, though.
It's science fiction. It's just mad engineering.
The Millennium Falcon wishes it has this level of engineering. You know, that thing looked like it was held together by gaffer tape compared to this.
Because it was.
It was. I always find that really crazy about like space movies. When you get like the old banger, you know, like it's supposed to be like an old rundown car, but like it's the pinnacle of engineering because it can go into space. Do you know what I mean? It's crazy.
Yep. So yeah, it's a cool piece of kit. It's grabbing a bunch of data and it's processing them. It's got natty data pipelines that take these observations and like it's got like stuff. There's a lot of cool software on the front end on like figuring out where those 5,000 robots look. So there's some cool like optimized software there. And then there's take all of these like multi-spectral images and process them.
Yeah.
So it's from a like engineering perspective, from a software perspective, it's really cool stuff.
And that kind of explains why the team is so large, because there's so many different facets. I always love when I watch like particularly like modern sciencey videos, there's always that bit at the end of the video where the person comes in front of the camera and says, this is why we need your unique expertise to help out with this project. Because like it doesn't matter what your expertise is, you would be able to find your niche with a project like this, right?
Yeah, so even in this, probably not doing it a service, but there's like electronic engineers, computer people, there's software engineers, there's optical engineers, then there's, and that's just the engineer side, then you've got like scientists and theoretical people and so
and
then
it needs to be manufactured,
and then there's even non-STEM stuff.
Yeah. It's crazy.
Manufacturing.
It is wild to me.
So it's a huge collaboration just between a bunch of institutes. The program is, so this is end of first year, but it's expected to be a 5-year data collection period. So
tune in 2029 when we look at the results.
hmm And so they're so it's a 5-year program. So far they've surveyed a lot of stuff. So they've surveyed I think it's about 5.7, was it million or billion? Maybe it's million. Let's assume it's million unique galaxies and quasars. And they gave a field of view that they've surveyed. But even what they've surveyed so far, is like an order of magnitude, or at least it's on par with
Yeah.
existing surveys that they've done.
Yeah.
So it feels like the impression I get from these types of large sky surveys, so like the equivalents that you may have heard of, would be the Sloan Digital Sky Survey. So that's SDSS, which is referred to in the paper.
Yes.
SDSS.
I think that might be the
also...
only one I've heard of from the paper was Sloan. But like
They
heard of, don't know anything
Mhm.
about, right?
Yep. They also did within that survey, they did like a subpart of that, which is a baryon oscillation spectroscopic survey, which is quite similar to the measurements done here. But the impression I get is the limitation for building better models, better measurements here is just gathering more and more data.
Yep.
So where they've got...
Sorry, I was thinking, when I was thinking about sort of, again, I was watching one of the YouTube videos. It's way easier to digest the information there than a paper for me. One lady was saying that they just have loads of data, and when we see it, sort of the final product, the notes, the results, that's like a distilled version of what
So
they
distilled.
have to. And it got me thinking, like last week, thinking about like imaging, when we talked about imaging in the previous episode. Would stuff like that ever be useful? And then that made me think about what you said of like, if it fakes it, is the data even data anymore? It's just, I love it. There's so much to think about, man. So much to think
Yep.
about. There's so many layers of complexity when you start talking about this, and I do feel like a little bit of a noob, I must say. But then, like, I have to sort of check myself and say, no, this is like cutting edge stuff, and actually, the fact that I'm even looking at it as a layman, that probably puts me, in more understanding than most, which I think is nice. But boy, it just boggles my brain. It really does. That's what the subtitle of this episode is going to be. Callum's brain gets boggled.
Let's do it.
Yeah.
Nice. Let's try and step back to paper. So we've talked about the hypothesis is, if we look at a bunch of things in the sky, we'll have a better idea. We'll be able to understand the cosmological challenges that we have at the moment, which is like, is the universe expanding at a changing rate? What's the expansion rate today? So they're the two current questions. They're doing this by looking at lots of new but old things, but things like in the past. So they're things further away from us, which just inherently by the nature of physics means that they're in the past. So they're sampling things up to 10.5 billion years ago, which is nuts. And I just wanted to step into a little bit what these baryon acoustic oscillations are.
Yes, please.
What did you figure they are?
Not got a clue, mate. I'm assuming a baryon is some sort of particle.
Baryon is normal matter.
Okay.
So
oscillation is a wiggle.
Stuff.
Oscillation is a wiggle.
That is, yes.
So it's something about wiggling.
Yeah, it's wiggles.
That's as much as I've got.
I assume the audience for this paper is
not me.
Not us. This isn't meant to be your public outreach paper. But if you scroll to, it says page 1 at the bottom. So this is in the introduction. So second paragraph. I was going to link it to you when I was prepping for this, and I thought
page 1 introduction. Page 1 introduction.
Yeah.
Because you knew I wouldn't read it.
So second paragraph here, we can see there's a sentence that starts very simply. Very simply, acoustic oscillations in the baryon So this is sorry, I missed this. This is explaining what a baryon acoustic oscillation is.
Uh-huh.
Very simply, Acoustic oscillations in the baryon photon fluid in the pre-recombination universe imprint a characteristic scale in the clustering of matter. This is manifested as a bump in the two-point correlation function of matter, or equivalently as a series of oscillations in its Fourier transform, the power spectrum. This keeps going. How very simply is that?
It was very simple.
It
Very
tickled me.
simply. That.
Very simply.
What were they thinking? Right. So on the peer observation, just take out the very simply
Yes.
on the peer review.
You don't need that. We don't need to condescend the reader.
Very simply, acoustic oscillations. I can't even read it without thinking.
So it took me a moment to go through this. I had
That's
to check some
crazy.
external resources too. But what this is initial universe, like pre-Big Bang. It does this Big Bang thing, and it leaves a pattern in the universe. So there is the cosmic microwave background radiation. So there's just like a large-scale pattern over the universe that we can see, and it is caused by, well, it's just a remnant of like the explosion. It's like an echo from the original Big Bang. Like there's a sequel.
Can't wait for the sequel. What about the prequel?
Now that is a good question. So there's this pattern from the Big Bang, and that's just a thing. So when that's also radio. Weren't we talking about the your birds flying on a screen, like the old CRT
Static.
monitors?
Yeah. Static.
Yeah, static. Why were we talking about that last? Did we already talk about the CMB?
CMB. We haven't talked about CMB.
Cosmic microwave background radiation. Because that's what causes it, right?
We haven't talked about that. No, is that what causes
I don't want to
static
talk
on the screen?
I thought it was.
I've never heard that in my life. But if
Maybe
that's
I'm talking
true,
rubbish.
that's mad. I'm gonna just, if that's true, that's mad with a little asterisk. We don't know.
We don't know.
We might be chatting complete rubbish.
Anyway, so that is like a cosmological remnant thing, and so this is similar to that. So there is from the Big Bang there is remnant structural patterns that you can observe from like galaxies, and it provides, and it's a known like length or scale, if that makes sense. So if we want to do this like expansion of the universe measurements, we're looking at different points in time, different points in space. What would really help is if we had some way to calibrate those measurements.
You love a calibration, don't you?
And this is what this is doing. So this is, you can think of this as just like your length scale in like an image, and so you know that your distance scale or your length scale can be calibrated to this baryon acoustic oscillation.
Right.
Kind of it. So you can.
It's like it's like when you look at a microscope image and it has the little bar that says 1 micrometer.
Exactly it.
Yeah. Okay.
Yeah, that's exactly what it's doing. So, very simply, it's a ruler.
Why didn't they just write that?
Yeah,
very simply, it's a ruler.
It kind of does. A characteristic scale in the clustering of matter. It's a ruler. They do say standard ruler down the line.
They do,
but it wasn't very simply. And you can so they're looking at they're using this standard ruler, and they're looking at all of these galaxies. They know their redshift, and they're looking for each of those. What's the expansion for each of those? So what's the expansion in the line of sight? So I forget, is that transverse? Maybe. No, maybe not. That's like the line of sight expansion, but they're also looking at like the transverse or tangential expansion. So they've got two planes of expansion. They're looking at your baryon acoustic oscillation constraints, what that could be, and then from that you can sample all of your galaxies and figure out each of these different points in back time what the expansion is.
It's just many layers.
Many layers.
Very simply, it's many layers.
Yeah. Yes. God. So that's what I had in method. You've got BAOs, and that's it. There's a bunch of other stuff going on here where they are. So they've built a new like analysis pipeline, and then they've said, well, to verify that, we're going to take some existing data that's already been processed. We're going to pass it through our pipeline, compare it to what those previous results are. So there was that type of stuff going on. So it's nice. Here's our new thing.
Some nice scientific,
as well as some new measurements.
Yeah.
So there's nice scientific method there. There was also, I think they stated it's a first for these types of sky surveys. There was a blinding of the catalogue. So you could imagine, I'm assuming, this is my inference here. You could imagine if a person doing the analysis had some preconceptions about whether or not they think the universe is expanding, slowing down, or doing this type of behavior, and they know like your x variable is like a redshift, and then they're calculating your y variable, which is a like expansion in some plane, that they might alter or introduce some biases to the
which is the
analysis.
nature of human beings, right?
Just human nature.
We introduce bias.
They love bias. So to account for that, they blinded the catalogue. There's some details about how they blinded. They had some like arbitrary random numbers to things, and then took them off when they unblinded it. But to initially, like an initial phase of their analysis was just only working with a blind catalogue. So they do their analysis.
I mean, it seems smart,
try and figure
right?
out some stuff. It's pretty good, and they did a lot of permutations of stuff to understand what the like bounds of uncertainties would be for their measurements. So you can see I can't even think what figures. I'm going to scroll right down here. It's probably in section 7. Section 7.
Just give me a page number and I'll meet you there.
Let's say 40 or something. Oh, no, I've got it. Figure 5, 35. So this is the sort of thing that we've got here. So we can look at some results pre and post blind, or pre and post unblinding. And where here we got a bunch of wiggles. They mean some things. I couldn't tell you what they really mean. But they those shaded regions
simply,
are
very simply, they're wiggles. They are wiggles.
Those shaded regions give an idea of what the uncertainty is that they evaluated in their blinded evaluation period.
Right.
Then they unblinded it, and they did a little tweak to how they were doing some of the analysis, but they justified it with saying we were going to do that anyway. So that was nice. So they got cool blinding stuff, some stuff about covariances, but
graphs are cool. Very simple.
Yeah, so
great.
Lots of cool plots. So I mentioned at the top end of the podcast that I had some preconceptions about cosmology. So I did a cosmology module back in my master's, and I can't even remember what they were teaching us, but my takeaway from that was the uncertainties are just gargantuan. Like, I wasn't even on like a thing with uncertainties at that point of time. I wasn't the metrologist I am now. But the idea of here's my, I think it was like the cosmological constant or something. There's like a lambda, and it's like this number, like 67 plus or minus like 20 or like 200 or something. It's like a really, really big uncertainty, and they're like, see, we got it, but there's a really big wiggle room. I definitely threw shade internally to the field of cosmology, because just like, how can they do anything? This is like they're doing the best they can, but
well, like you said right at the top of the podcast, all they could do is look.
All they can do is look. Yeah, they got like they're not dealt the best set of cards. They can't do.
But also, they chose to go into that field, I imagine.
Yeah, all right.
It's like me when I complain about being a teacher. Well, I didn't have to do it, did I? I didn't have to. I could have gone worked at Tesco.
It's not bad. Yes. And so we can see it. Like I've scrolled down to like figure 7 at this point, and you can see they've got uncertainty bars. Do love uncertainty bars. And if you just look at like an arbitrary dot, it's like dot and then a reasonable sized uncertainty. So uncertainties are tricky to do, and that's the whole point of their like blinding and validation.
Those uncertainties,
lots of permutations.
I mean, I'm gonna be honest, I don't really know what I'm looking at here, but the lines don't look massive. Like, it doesn't look
That is my point. Yeah,
crazily uncertain, right?
they kind of look reasonable. They're
Yeah,
saying, here's my points, here's a little window of uncertainty. I'm going to draw a line through them. And you're like, yeah, I believe that line. That's a
yeah.
believable line.
So is a potential takeaway that we as a species are getting better at making these observations, even in the however many years since you've done your masters, or is it, what makes this more certain?
I think I was just ignorant in my masters.
Right, fair. Hey, that's
But
really,
yeah,
really
like
good
this is pretty
introspection,
good.
mate. That's good. That's great. That's personal growth right there.
Got to admit when you're wrong, which is a
Absolutely,
lot.
absolutely. And it's hard to do. Again, going back to
Yeah.
being a human with bias, humans are also, I think, inherently sort of protective of the ego. Not
Hmm.
even to say that people are like egocentric, but sometimes it can be difficult to admit when you
Yep.
do something wrong. Like if I could go
Yeah.
back in time and pay more attention at university, shall we say,
Hmm.
I'd I wonder what would be different. But hey ho, it's good. It's
Yep.
good introspection. I'm proud of you.
Thanks, man.
You're
Not what I
welcome.
was looking for, but thanks, man.
You're welcome.
Just some more plots. Figure 15, page 49.
I'm going. 49,
Oh yeah.
48, 49. All right.
So
I'm on
this is,
15.
to me, this feels like the meat and potatoes. And if you're going to write your clickbaity article title, this is where you see it.
Okay.
So what we can see here is we're plotting if we just look at the first like 3 boxes, because I didn't pay enough attention to figure out what the fourth box means, but it's some ratio of ratios of ratios. But those top 3. So the top box is talking about the co-moving distance. So when you were talking about your chocolate chips and a cookie, this is that type of measurement. So the distance between things, the co-moving distance. Second box is the Hubble distance. I didn't figure that one out. And then the third box is the DV is the, what is it, the spherically averaged distance. So I think that's if you, rather than thinking about things like transverse expansion and line of sight expansion, this is just assume, like, make an average of a sphere.
Right.
So they're all kind of the same sort of thing, saying expansion rates over time.
Okay.
So we're seeing on the x-axis is redshift, but let's maybe think of this as billion years ago or time since
Yep.
now.
We've already established that they're correlated. Redshift is correlated to time ago. Okay.
And if we look at so what we can see is there's some grayed out plots, which are the previous Sloan Digital Sky Survey results. There's DES year 6. I'm not sure which date set that was from, but I'm assuming it's dark energy survey released in year 6. And then the remaining coloured plots are the different bins. So they separated the evaluation into different types of galaxies. So there's like the newer stuff, which is BGS, Bright Galaxy Survey. Then there's the old galaxies, which would be your luminous red or LRG galaxies. So they're like big stars, but really old, but quite red. And then there's the ELGs, Mission Line Galaxies. They're just even older stuff, but it's kind of like different periods of time. And then the really, really old stuff is like quasars. So they're supermassive black holes spewing out really bright energy as a bit like a standard candle. So what we can see here is if we look at the I guess maybe if we look at the second box.
Yep.
So there is, if we just look at the coloured points, so what they're saying is everything's close to 1, which is saying it's mostly static, or it's not changing much over time, I think is what that's saying. And then if we look at the yellow plot here, so that's saying more recently in like the 0.5 redshift, which is about 5 billion years ago. I guess that's corresponds to. It's saying that the rate of expansion was lower. Yes. So it's saying that the rate of expansion is lower than previously estimated,
Right.
and so the rate of expansion is slowing down. And that's kind of like the higher level clickbaity title. Everyone's got it wrong up to now. It's actually slowing down.
Right. I mean,
Boom.
I am confused.
So, orange dot there
Yeah.
being lower than a line says it's slowing down.
Right.
That's what it says. But if we and that's kind of it. So from a if you were to be a bit of a cynic, you could say, yeah, well, that's just one measurement.
Yeah. I
Come
think
on.
I'll adopt
How much-
that pose.
Yeah, how much faith do I have in one measurement? So like all this previous survey stuff, it said it's pretty constant, but now you're saying I've got this one measurement and it's slowing down, really?
Which I think that's probably a fair comeback.
It's a
Until
fair
there's more
comeback.
data, right?
Until there's more data, so this is only year one of the release, so naturally it will evolve over time. There's also, I guess the other aspect of that is we were already saying that this is such a distilled value. So like so much stuff has gone into this one number
Yeah.
that you can just say, yeah, it's 1 point, but like it's lots of really good points into one.
Has gone into 1 point, yeah. Okay.
Yeah, and I think the other thing to highlight would be top box here. So there is a broadly all of the measurements being close to one says everyone's all in agreement between different sky surveys. What we can see in the top plot for the luminous red galaxies between 0.6 and 0.8 redshift is there's quite a large disagreement. So like with it outside of their uncertainties, there's a huge disagreement between these DESI measurements from year one and the is it the SCS, the Sloan Digital Sky Survey. So there's a remark in the paper and they say we think it's because of this, or well, they say we think it's because of this, and they also say but we're really confident on our data and we validated our data on the SDS survey. So like they're confident with their data, but there's a big discrepancy there. So yeah, there's a couple of question marks coming up from
but
that aspect.
I imagine those, well, I don't imagine they will be answered, but we would know more as the project continues, right?
Yeah.
I have a question. Why didn't they put this telescope into space?
That's a good question, and I thought about that too. Why do you think they didn't do it?
Cost is why I think they didn't do it.
Cost is a good one.
Also, I imagine it needs a lot of it might need a lot of repairing. I imagine there's a lot of parts, so that's gonna.
I think it like top level is cost and complexity. Yeah, if you were to pop this in space, it's just tough, man.
And then one of the robots breaks. Yeah.
And the timescales of putting stuff in space is just so slow. So like maybe something like this will be in space at some point down the line. Like think how long it took James Webb to be up there.
Yeah.
Maybe it will be. It'll join that type of mission, but it's just really difficult to get things into space. So having it on the ground is difficult because you've got to account for the atmosphere doing weird things and
wind,
whatnot.
rain, weather.
Yeah, it's just difficult. I did like so reading section 2 of the overview. They said for readers less interested in the method that just want to know the results, read sections 7, 8, and 9. Okay, all right. And they said also look at table 18. So if you can scroll down to table 18, just on the next page.
Table
there
18. Final
I'm not
summary
gonna
of
say
the
anything more than that.
distance scales from its fits the postings.
But from their perspective, that's the meat and potatoes of the paper.
Right. Is that just the graphs, basically?
It's basically it's the graphs that we've just seen. So yeah,
Yeah, I mean, what a fantastic meat and potatoes! I can tell you a lot about
epic
that. Oh my god!
So this is such a big field. They've released a bunch of papers around the same time. So they say that this is like how we got our numbers. But then there's a follow-on paper, well not a follow-on paper, but a related paper where they talk about the cosmology that these measurements imply. So for listeners or readers, watchers, interested, there's more material if you'd like.
Definitely more.
So taking these numbers and then applying them to like Hubble constant stuff is.
So do we have Do we want to talk about the conclusion? I'm conscious of time because you said you have a meeting.
I'm conscious of time too. Yeah, let's work on that.
Let's
So
skip to conclusion and final thoughts, and then we'll wrap up in the next 5 or 6 minutes. Sound
yeah,
good?
let's do that. Yep. So conclusion of the paper. It's kind of the stuff that we've talked about. They've looked at lots of galaxies. They've looked from up to like 10.5 billion years ago.
Mhm.
They've surveyed a lot of the sky, but not all of the sky. They're going to capture more of these galaxies and quasars down the line. Initial measurements suggest their operational pipeline is hunky-dory.
Yep.
It's rock solid because they've proposed some evidence for that. But initial measurements for the expansion is different to
Weird.
what
not what they might
other
have
people thought.
expected. Yeah.
And that's kind of the takeaway. And it's a bit of a watch this space.
It's exciting.
Takeaway.
So
It's
let's
really exciting.
let's talk then final thoughts and sort of takeaways from the episode and the paper as a whole. I'm going to get philosophical, probably.
I'm sure you got philosophical on previous ones,
But
right?
I always do. I lead with my heart, not with my mind, Jamie. But what your takeaways? I'm assuming is going to be thinking about your master's ignorance and sort of those learning.
Yeah, you can just do it for me. Yeah, pretty much.
Sorry,
Yeah.
I didn't mean to take your thunder. Take it away. What are your final thoughts?
That's it. That's it, basically. I came into this ignorant. I came away just astounded by the just insane prowess demonstrated here. Epic collaboration between science teams, engineering teams, people just getting it done. Scientific rigor. I don't know. I got nothing. No skin in this game.
I'm gonna
like most games, but
I'm gonna piggyback off of yours for my final thoughts because actually.
please.
You talked about the collaboration and the human effort, and I just stuff like because when you're an adult in 2024 and you see the news and you do this, that, and the other, you lose faith in humanity. I find. I don't know about you, but I lose faith.
I don't pay attention to the news, so
I try my best.
faith in humanity's still there.
I try my best not to, mate. But like sometimes it's really challenging. There's obviously things going on in the world at the moment that are awful. And when you work in a school and the kids are asking, and if I don't know anything about anything, it can be challenging, right?
Yep.
And being in a school as well, I have to be unbiased, shall we say? Which is extremely challenging, and it makes me sometimes I get very sad thinking about sort of the state of the world, right? But then you look at collaborations like this and you're like, damn, maybe we're not that bad. But then I just wish people would listen to scientists. I really do, because I think we would live in a much better and fairer world if these brilliant and intelligent humans could make some decisions. Do you know what I mean?
It would be a novel place, right? It would be novel.
It would be novel. It would be
Yeah.
brand spanking novel. That's for sure.
Yeah, that's an epic takeaway.
That to me. I'm just astounded by it, by the power of humans working together as opposed to working in opposition. I just think it's brilliant.
Nice.
Great.
This has been great. I've really enjoyed this.
Me too. We're cutting edge, and I was really worried that we would flounder, which maybe we did a little bit, but I had fun.
Absolutely, we did.
I had fun.
But I had fun.
Good.
Hope you had fun, everybody else.
Yeah, I hope so too. Tune in next week to watch us flounder some more.
Yeah. Where can people find us, Callum?
They can find us wherever they find their regular podcasts, Spotify, etc., etc. If you want to catch us on YouTube, we're at Osmosiscast there. You can drop us an email if you've got a paper that you want us to have a look at.
Nice.
Yeah, I think that's about it. Anything else to say, or are we good?
I was going to drop a couple of bonus links in the show notes, so check them. If you just want to look at some pretty videos of what this DESI instrument is, yeah, check out the show notes. But
perfect.
I'd recommend. Well, of course I'd recommend it, but I'd recommend looking into some of this work. I think it's exceptional effort. from many parties.
What a lovely final thought. Thank you very much for listening.
Thanks a lot, everybody. Bye.
Goodbye.